remember yesterday we said, okay, there's this model called F is equal to MA. And if you look at that, you may imagine that this model does not contain any parameters or fittable constants. But you would be wrong, because you would be forgetting that there is a fittable constant over there. So you will remember, hopefully, from CIR, that not all unit systems have this simple version of this equation. Okay, some unit systems have that big G in that location. So that equality has a 1 in that location because we've chosen our units in the SI to satisfy that relationship. If we had chosen slightly different units of mass, right? So F is not equal to MA for F in Newton and M in pounds. Does that make sense to everybody? Like that formula doesn't work out numerically. If I just plug in M in pounds and acceleration in meters per second squared, I will not get a force, the correct value for force expressed in newtons. Does that make sense? Okay, so it only works, so we have actually fitted that, but the tuning constants are embedded in our dimension system. Okay, so keep in mind that even something that seems like as first principle as Newton's law is effectively not as pure as you would want it to be. So we've got this first level model, which is a theoretical model, and this is the stuff, theoretically, the stuff that is in your textbooks under like fundamental laws of nature. This is like Newton's laws or like the conservation laws or that kind of stuff. Like we wouldn't say, oh, in is approximately equal to out at steady state. We say that it is definitely as near as we can tell. Now, I'm going to problematize it for you. I just want to remind you that even those things that you think of as being really, really deep down fundamental, we know, for instance, that Newton's laws are an approximation, right? That they are not true in the capital T sense because Einstein. Okay? So F is only really approximately equal to MA for small values of A and small values of M. Right? So for large values of M or really large values of A, that relationship no longer holds quite as strongly. In is not equal to out in nuclear reactors, right? Nuclear reactors create energy from mass. And so the mass that you put into a nuclear reactor is not the same as the mass that you take out of the nuclear reactor. Okay? So I just want to remind you that you kind of know this, but we pretend that kind of what fundamental is what I'm trying to explain is a little bit movable. So we choose to say, in this subject, we will never talk about Einstein's laws, right? We'll never be at relativistic speeds. We'll never be moving mass to energy or the other way around. We'll assume that kind of that's the top level in the same way that, so that means conservation laws are fundamental laws in this subject. And kind of Newtonian mechanics are fundamental laws in this subject. So that's like level 1, that's theoretical models, right? Then we have what is called empirical models. And the empirical models are the kind of models that I'm going to have you fit onto the cup results that we, or the cup experiment that we did yesterday. So I'll switch over to what those things look like in a second, but you can imagine that I can take any set of dots and I can go into Excel and I can fit a curve through Excel. And Excel isn't using any special knowledge about the world when it's doing that, right? It's taking some kind of mathematical curve. I can select from a drop down. I can say I can want to fit a cubic, or I can fit an exponential, or whatever. I can just kind of play around, see what kind of curve appears to approximate the points well, and I'm not making any positive statements about kind of the nature of reality, you know, like I'm not making broad claims that this will be true over all times and for all men. I'm just saying, well, these data, this particular mathematical formula has the property that it goes through all the data. Right? So that's empirical models. Empirical means in this context, it's also kind of one of those loaded words. Empirical refers to the idea that you are making measurements. Right? It's the empiricist viewpoint where we're making measurements to know about the world. We're not sitting in our couches and imagining what the world is like. So stuff like geometry and mathematics, mathematicians can do math without measuring things about the world. And geometers can kind of postulate theories about the shapes that they think of without measuring the world. Empiricists have to measure the world in order to fit their equations, right? The equations don't work if I don't have data to drive them. Then somewhere in between, it's listed as point number 3 in the textbook, but kind of, if you think about it, it's a blended approach. It says, let's just say that f is equal to k times ma. And then we'll do some experiments to figure out the value of k. Right? So this is known as a parameter. And you will also hear me use this word from time to time of a parameterized version of an equation. Right? So we can say, well, the original version of the equation looked like f is equal to ma, but I can add some extra parameters which you should be familiar with from CBI, where maybe you want to experiment a bit with the order of stuff, right? So maybe you want to say, oh, let's add maybe it's like a to the power n. Who knows, right? Maybe it's not quite just f equals ma. Maybe it's like k times ma to the power n plus c, right? And then we can kind of use the data that we have to figure out what those different parameters are by either just eyeballing it, in other words, moving the values and kind of seeing what values seem to fit the shapes that we're seeing, or by kind of solving the equation and kind of trying to figure out what the average parameters are. There's a lot of different approaches. We're going to go into a great deal of detail about systematic empirical models later on in study theme 7. Chapter 6 of the textbook. So if you want to skip ahead, that's perfectly fine with me. But for now, we're going to focus on the idea of how do we model things that we are able to describe on this theoretical level. Now, why did I talk about Einstein and Newton and all of these things? Why didn't I just say, here's the theory? I don't want you to imagine that these particular theories have any particular privileged position other than the fact that they are known shapes that describe the world around us. So something like Newton's law, again, I want you to remind yourself that that is an approximate thing, right? When we write down equations that describe what we observe in the world, we do not fundamentally have any way of knowing whether they are true with a capital T. One of the big things about science is we can say, I have this hypothesis that it works this way, and I can do experiments and I can avoid being proven wrong for a certain amount of time. But experiment can only ever prove you wrong. It can never prove you right. And so I'm doing that little intro to just say when we look at the cup data now, there's no privileged model that you can say, oh, well, I looked in Perry, and I found the model that Perry says is going to describe this behavior, and so that's the right model. That's the correct model. I'm saying this because this is the challenging part of modeling in this subject. Unfortunately, the reality is there is no easy way to say that you have correctly found the model. Correctly predicting experimental results is not evidence, or it's not a proof that your model is right. It is evidence that your model isn't wrong. And that's a super important thing, right? That's incredibly important. Models cannot be right, they can only avoid being wrong. That's fundamentally the thing that we're trying to do in the subject, is we're trying to set up models, not that are the right models. And why I'm saying this is you will find in the tutorial problems, in the semester tests, in the examples that I do, you may differ from my decisions. And I want to warn you, I want to raise a red flag and say, when you have a different view from me, this does not guarantee that you are wrong. Right? So if I'm doing a math thing, if I'm saying 2 plus 2 is equal to 4, if you get a different answer from me, you are wrong. 100% guaranteed wrong, because that's how math works. Right? We've got axioms, we've got rules repeatedly. If I give you a mathematical sum like 2 plus 2, I give everybody in the class 2 plus 2. Everybody who gets 4 is right. Everybody who didn't get 4 is wrong. Right? If I sketch a system for you, and I say, let's set up a model, and let's say a theoretical model even, of this system. If your model equations differ from mine, does that mean you're wrong? No. I'll get different model equations from all of you. This means when you have access to a solution, if I have a worked solution that I do in class, if you look at a worked example in the textbook, and you're asking yourself, but wait a minute, I got a different answer, and so I must be wrong. You're approaching it incorrectly. And so I'm going to try to highlight ways, like successful ways, to judge whether you have an acceptable answer. And I will never talk about you being right or wrong. Models aren't right or wrong, they are just useful or not, given what we're trying to achieve with those models. Okay? And so you should be learning about the reasons why you are trying to set up this model, and then evaluating the success of your model against the original reasons. You should not be thinking about, well, my friend got this other answer, so one of us must be wrong. You can both be right. It is possible, right? Just having different answers is not evidence that one of you is wrong. So that sums up much of the kind of overview idea, and that link to parsimony. Just that one word, right, opens up a whole line of thinking with how do I judge models. Parsimony is one way to judge. If I have two curves, I'm going to use now, sir. If I have two curves, if I have these two curves, right, and the one curve is something like this, and the other curve is something like this. Right. I would prefer the simpler version. I would prefer the one with the fewer fittable parameters, purely based on parsimony. Now, notice, I'm not saying definitely the exponential model is right. Me personally, I have a strong suspicion that if we were to do a theoretical model, it would have that kind of exponential nature. But if I'm trying to merely do interpolation, if I'm trying to figure out like what would be the values between the values, the polynomial fit is perfectly usable, right? It's very useful if I'm trying to figure out what's happening in between points to do linear interpolation, for instance. But we definitely don't think that like things in nature are made up out of piecewise straight lines. But everybody here has done linear interpolation on tables, right? That's a model, right? You've said, when there's a point over here and there's a point over here and I have some unknown value and I want to figure out what's going on, as a first approximation, I'm just going to imagine that those points are connected by a straight line. It's a useful model. Even though nobody here imagines that those thermodynamic curves that you've used linear interpolation on actually look like pieces of lines, right? Usefulness is much more important than correctness when we're trying to develop useful models. Right, So you can have a look at this, but there's this quote by Box that says exactly what I've just said, which is like models can be either useful or not. They can't be right or wrong. Okay, so that's kind of what I want you to take out from these general modeling principles. We'll be talking only next week about the analysis of models that starts at 2.3. So even later today, you're going to be engaging a little bit, running code on the CUP data that we've collected, and you're going to be trying to fit models to your personal data and everybody else's. I'm going to put a Google Drive link up on ClickUp where everybody's files are. They need a little bit of cleaning, like I mentioned, so I'm going to go through that now. And I want you to just engage with fitting a couple of different kinds of curves. I would like you not to try to be right. You know, I mean, actually, if you feel moved to read ahead in the textbook and like really do a proper theoretical model, that's absolutely fine. I don't expect you to do that tonight. I'll be going through that example in class as we go along, and we'll fit a couple of different curves and see how well they work. The idea here is that we'll see that obviously every one of you can fit a polynomial model to your CUP data, to your draining CUP data. But we're hoping that we can get a parsimonious model that's one equation or a small number of equations with a small number of parameters that can explain all of the observed data. And we will say that that model is much more useful than having to have 120 models, 120 different equations, and that one has the property that it can only explain the data for that one CUP.